All right, welcome back. Now, next I'm going to show you all the different types of example that utilizes all the non-parametric tests using sign tests, Wilcoxon sign rank test, and then lastly Wilcoxon rank sum test. Right. Now, first example is a motivation example here. Okay. Now we are dealing with carrying out non-parametric tests for single sample for the first example here. Now the research activity involve the following survey. All right. Now some of you might want to carry out a survey to find out whether the president's performance is above average or whether he's doing his job or not. So the question for the questionnaire is the president is doing the best possible job in the circumstances. All right. Now please choose the following responses. Now that will be the survey questions that will be delivered to the respondent. Now there are like seven responses that the user can respond to. It's either agree strongly, agree, inclined to agree, have no opinion, inclined to disagree, disagree, or disagree strongly. Right. Okay. So now you are going to test the hypothesis. The president's performance is generally disapprove of. Disapprove of, right? So whether you would agree with this statement or not, whether the president is not really doing his jobs properly, for instance. Right? Now, what happens is that once this survey has been carried out, the sample has been collected. Right? So you can see that these are the samples collected from all the respondent. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 responses here, right? But of the 12 responses here, you can see that 4 does not really have any opinion, right? 4 is considered as the center of the data itself. Right. So in this case, in order to carry out the test, we can actually ignore or omit the response that has no opinion, which is 4 here. So we can actually exclude this response 4 because it is the same as the um, response of having no opinion, right? So before we start to carry out the hypothesis test here or non-parametric test, we have to write down the hypothesis statement here. Right now, the null hypothesis would be now generally the people would usually we will start off by saying the people is likely to agree, right? Is likely to agree. Um, so the people is likely to agree and disagree. Right. So the people are likely to agree or disagree with the statements given here. Right. So I just put it short here. Right. Now, whereby the alternative hypothesis would say that the people is more likely to disagree, are more likely to disagree than agree. Right. Take for instance, this is our hypothesis statements here. Right. Now, more likely to disagree. because our hypothesis statements stating here the president's performance is generally disapproved of based on the responses. So you can also write it down as the people is more likely to disagree than agree. So disagree here would mean the response value would be like anything greater than 4 then. So this is like response of 7, 6, 5, 4, 3, 2, 1 here, right? Now to carry out this sign test, we can ignore the center of the data here, right? Because this is the respondent that does not have any opinion. So we can actually ignore these two sets of data, right? Therefore, the sample size now will become 10 instead of 12. So the sample size will become 10 now instead of 12, right? So I hope that is clear. Now, just at a glance, just as a glance itself, we notice that like you have one, two, three. Okay, three respondent that would agree, that would sort of agree that the president is uh, doing best possible job, and then the rest would disagree. Right. So just at a glance, we can say that most of the respondents would generally disapprove of the president's performance. So therefore, we can conclude that just by looking at the data itself, generally speaking, we can say that the president's performance is generally disapproved of. So that means the people is more likely to disagree that the president is doing his possible job. All right. Okay. Now I hope that is clear. All right. Now I'm going to show you two methods how we can carry out this sign test here. Now, based on our hypothesis test here, right? Now, the first method is okay. We can actually um, put a sign. So that's the main reason why this test is called a sign test here. So we can actually put a sign onto all the responses, right? Okay, so you can see that here um, the plus sign and the negative sign has been placed for all the responses here, and the negative signify that any response that is below 4, below 4. So the 4 is something like the center of the data or hypothesized value here, because we state that in our null hypothesis the people is likely to agree and disagree. It's likely to agree or disagree. Sorry, it's agree or disagree. Right. So therefore, the hypothesized value will be a 4 in this case. Right. So we are actually comparing for each of these responses whether that observed value is above or below. If you see a negative, it means it's below 4. If it is plus, it means above 4 here. So here we have 1, 2, 3, 4, 5, 6, 7. So we have seven um, 7 sets of data observation that is above 4 here. That's above 4 here, right? Which means uh, uh, most of the responses would say that they disagree that the president is doing his possible job. Right? Okay, so how are we going to carry out the sign test using this sign that we have already set up here? As I mentioned before, those that does not have sign, which means the median itself, in this case is 4, we will ignore that in our test here. All right. Now to do that, you have to carry out the sign test. You have to count um, how many that is greater than 4, how many that is greater than sorry, how many greater than 4, how many less than 4 in this case, right? And then next, before we continue on, we need to carry out a sign test at 5% significant level. So therefore, uh, the type 1 error has been specified for us, which is 0.05 here. Now, for this critical region, it is stated that we need to find the probability of uh, the rejecting null hypothesis, but null hypothesis is actually true. So the percentage of rejecting the null hypothesis, yet the null hypothesis is actually true, is 0.05%. So we want to make sure we don't actually reject null hypothesis by chance. So that's what it actually means, right? Now, in order to do that, okay, we will have to have now generally I'm going to write it down here. Alpha is actually probability of rejecting reject, I make it short here, reject h naught, um, even though h naught could be true. So we want to make sure this probability is as small as possible. So how can we actually reject um, null hypothesis? Okay, if you want to avoid rejecting null due to chance. Right? So we're going to reject null. In order to reject null, okay, or accept the alternative hypothesis, we will have to have more people to sort of disagree. More people to disagree uh, with the response in this case, right? So more people to disagree. Therefore, I can actually write down in this case, we have to have more people to disagree. Okay, more people to disagree. Let's label X as number of people who who disagree in this case, right? Now I'm going to continue. All right, as I mentioned before, alpha represent the probability of rejecting the null hypothesis, even though there's chances that the null hypothesis is true. Okay, now in order to reject null hypothesis, you want to get as many responses that would sort of disagree disagree with the statement itself. Okay. Now to do that, before we write down the actual probability, here we are going to do a label. We're going to write down X represent, um, here I just make it short, number of people agree agree with the statement, right? Number of people agree with the statement there, right? So if X represent number of people that agree with the statement, so therefore our alpha in this case would be X would be less than equal to X here. So what we are trying to find is number of people that agree, right, would be as small as possible, as small as possible for us to be able to reject the null hypothesis. Or instead, you can say that I want to have more people to disagree, more people to disagree. But if X represent number of people agree, you want to have as few people agree with the statement so that we are able to have sufficient evidence to reject the null hypothesis there. So this is our key probability, and then this probability must be less than or equal to 0.05 for us to be able to reject the null hypothesis. And then this criteria will be our guideline to find out the critical region later on, right? So I hope you are clear with how the hypothesis statement has been set up, and then what does X represent, and then where is the critical region that we are interested to identify in this case, right? Okay, so bear in mind, X represent number of people agree in this case. And then based on the responses that we have one people, two people, three people. We have three people agree with the statement itself. Okay, so we are going to find the probability of these three people agreeing with this statement, and then we get to check whether this probability actually fall in the rejection uh, zone or, not, or rejection region, right? So I'm going to minimize this. Okay, we're going to come back here. So bear in mind, we have three here. So we're going to label that again. Okay, this one we have to ignore that. Okay, we have three responses that say agree with the statement there, right? So basically, your x is actually equal to 3 at this point. And then we are trying to find probability. Let's try it out. So probability x less than equal to 3, for instance. Let's give it a try from here. Now, probability x less than equal to 3 is basically probably x equal to 0, because this x represent number of people, so it should be a discrete distributions here. Px equal to 1, px equal to 2, and then finally you have px equal to 3 here, right? And then how do we find each individual probability? Now, since x represent number of people agree, then there will be a certain amount of people that disagree. So therefore, this is a binomial distributions. So these binomial distributions we can write as uh, binomial distributions with how many trials here. So we ignore the two that have no response. In this case, we left with sample size of 10. Probability of success is either the people agree or disagree with the statement itself. So therefore, it will have a probability of success of um, 50% here. And then by taking this binomial distributions formula, we are going to tabulate this probability here, right? Now I'm going to show you what is the result for this, okay, to speed up the process here. Okay, I'm going to pull this one down a little bit here. Okay, maybe I'm going to erase this one and write it down. Hold on, just let me clean this up. Okay. So bear in mind, we are interested to find px less than 3, because we have 3 responses that agree with that. All right. Now, yep, probability less than 3, but I think I accidentally chosen the wrong distribution. It's supposed to be a binomial distribution, so let me correct that. Okay, so binomial distributions, we have a sample size of 10 in this case. Our probability of success is still 0 0.5 here. So I'm interested to find out probability less than 3. What would that be? Probability less than 3 here would be 0 0.175. Is that correct? Just let me check. Is that correct? Okay, yes, it is correct. So probability less than 3 is 0.1719 there. All right. Now I'm going to write that down here. So you get 0.1719, which is actually more than that 5%, which is more than 5%. All right. Now, since px less than 3 has a probability larger than the significant level, therefore x less than 3 is outside of the rejection zone. Therefore, we does not have sufficient evidence to reject null hypothesis. Therefore, in this case, we're going to accept the null hypothesis. The conclusions would be the people is likely to agree and or disagree with the statement itself. Now that would be the correct conclusions that we should have. Right? Now I hope that's clear. Alright, now I'm going to show you the second methods, how we can carry out this sign test. Also using the same tool, it's just that the sequence or how we carry out the analysis is a little bit different, right? Now let me recap again. Generally, we're going to set up the hypothesis statement. This is our first step, right? Now, secondly, try to identify your significant level, which is usually given in the exam, alpha here, and then try to really understand what does alpha actually represent. So alpha actually represent type 1 error. It's the probability of us to be able to reject null hypothesis, not due to chance. Right. So in our case, if we represent x as a number of people that agree with that statement, therefore, we are trying to look for probability of x less than a critical value x here that will yield anything less than 0.05 for us to be able to reject the null hypothesis. All right. I hope that is clear. Binomial, this is a binomial distributions problem because we can either agree or disagree with the statement itself. And then by omitting the neutral re response, we only left with a sample size of 10 here. All right. Now next, by using all these informations, we are going to perform a trial and error here to determine the critical region. Okay, instead of using the p-value methods or the probability methods just now. All right. So we're going to determine our critical value or critical region here. To do that, now we're going to trial and error. So I'm going to write that down here. So we're going to use a bit of trial and error here. Okay, so I'm going to start off by, for instance, you can try px less than 1 here, for instance. Right, now by using GeoGebra in this case, so let me try out. Okay, so if you try, for instance, probability less than 1 there. Okay, so that probability would actually give us 0.0107 here. Yeah. Okay, and then I can try error for px less than 2. Okay, I can actually give that a try. So take for instance, if it's less than 2, let me see what do we have. Okay, I will have 0.0547. Now you can see that this probability is already exceeding, this p-value already exceed the significant level, already exceeding the significant level, whereby the significant level is supposed to be somewhere here. This part will be the rejection zone, but the value of 2 is already outside of the rejection region. Therefore, at this point, you can conclude that, in this case, you can conclude that the critical or the critical value, because this is discrete, so we use critical value or critical region, must cover the value of 0 or 1. 0 or 1 here. Okay, 0 or 1, whereby the x is a discrete value that represent number of people that agree with that statement. Now the rejection zone should cover a critical value of 0 and 1. Okay, now I hope that's clear. Now before we can conclude, we will have to come back to our data observation. We're going to count how many sets of data that is actually agree with that statement. So here we found that there are 3 sets of data that agree with the statement, and then we are going to check whether these 3 sets of data agreeing with the statement actually fall in the rejection region. Now we know that in order to fall in the rejection region, the number of people agree must be either 0 or 1, but there are 3 people that agree. So therefore, it fall outside of the rejection region. Therefore, we fail to reject, or we fail to reject null hypothesis, or we do not have sufficient evidence to reject null hypothesis. Therefore, the people is likely to agree and disagree with the statement here. All right. Now, I hope that is clear. These are the two approaches or strategy that you can use to carry out sign tests. Which one to use is actually up to you, because both of them yield the same result and they utilize the same probability distribution. Right. Now, I hope the uh, motivations question is clear to you. Stay tuned for the first example shortly. All right, welcome back. This is our second example. All right, let's read it through before we start. And ornithologist records the number of house martins, a bird species, per day flying over a headland. Her observations cover a sample of 15 days during the migration season of this year. Right now the following sample has been collected. Right now, for instance, on a specific day, there are 281 house martins um, flying over that headland that she is observing. All right, so there's a lots of birds actually. She must be using certain device to actually estimate the number of birds that actually fly over that region. Right. Now, records show that for several years, the median number per day has been 270.5, which means averagely there are like 270.5 house martins flying over that region. Now, 270.5 is just a mathematical value. Now, in general, birds cannot have 270.5, right? So this is just a average measurement. Right? Now, use a sign test to examine at 5% significant level, the type 1 error, whether there has been an increase in the numbers of house martin flying over the headland during the migration season of this year. Right. Now we're going to start off by writing the hypothesis statement as usual. So we will say that now the whether there's an increase in the number of house martin flying over. So we will say that the number of house martin flying over. All right, so the number of house martin flying over is 270.5. Let's assume that it does not change. Okay. Now, secondly, for alternative, of course, we will say that the number of house martin flying has increased. For instance, flying over has increased. Example has increased or is greater than 270.5. You can also say that. All right. So here I just make a remark. You can actually write as greater than 270.5 here. Right. Now I hope that is clear. That's how we set up our hypothesis statement. Okay. Now next, we will have to the first thing usually would be before you actually carry out the test is to write down because this is a binomial distribution for sure. Whenever you carry out a sign test, it's always a binomial distribution because that's the easiest distributions to use for this analysis. So we have to write down what is the definition for x here. So x actually represent number of observation. Okay. Number of observations greater than 270.5. Okay, so x actually represent number of observation that is actually greater than 270.5 here. So once you know what does the x actually represent, now we can say that, all right, now the x can be represented as a binomial distributions, and then we have 15 sets of data here. um, Probability of the number of house martins flying over is greater than, must be 50%. Less than also must be 50%. Right? So x represent number of observations that is greater than 270.5 here. All right. So therefore, the next part would be to identify uh, what type of test that you are carrying, whether it's a one-tail test like what we did just now, or whether it's a two-tail test, or whether it's another one-tail test, but the tail is on the other side. Okay, like just now we have done a left-hand tail. Now we are interested to see uh, if the number of observations x greater than 270 is significantly large for us to be able to reject our null hypothesis. For us to be able to reject our null hypothesis. Therefore, at this point of time, what we are interested to find is, in this case, it will be here. So I'm going to show you using trial and errors methods here. The functions here would be the x must be greater than x then, and then this region must be less than 0.05 since our significant level is 5 percent there. All right. So we want to find out the how many observations that would be more than that would be more than a critical value, and then the rejection zone will be 5% in this case, right? So anything more than this x value, we will have sufficient evidence to reject the null hypothesis. So if the number of observations that is greater than 270.5 does not exceed this critical value, then we don't have sufficient evidence to reject the null hypothesis. So I hope this part is clear to you. Don't try to memorize this sign here. Like the first one is x less than equal to, but this one is more than x. What we are trying to say is, do we have significant result to suggest that there are more number of observations that is greater than 270 there. Okay, so if we have, then we will be able to reject the null hypothesis. All right, so yeah, pay more attention to this part than what is coming on. Right, so what is coming on is very simple. Now using trial and error, okay, this is what we are trying to find here. So since this is greater than or equal to x, we are looking at the upper tail test. So this is upper tail test here. So on the right hand side, right? So we are trying to guess. You can use trial and error. Okay, so trial and error. We're going to try, for instance, let's try 13, for instance. You can try 12, 11, and so on and so forth. I also can't remember. So let's try out using the GeoGebra here. We have 15, so we're going to key in 15 here. And the probability of success failure still remain the same. I'm trying to perform an upper tail test, so it should be an upper tail test. I'm trying my luck here with 13. So if I use 13, right, the probability is actually equal to 0.0037. This region here, which is in the rejection zone. But we want to find the smallest value of x, where it's just about to enter into the rejection zone. Right? So I'm going to try again using 12 then. Let's see whether it works. Okay, using a 12. Okay, so using a 12, let's see. Right, using a 12, I will get a 0.0176 there. Right, using a 12 is 0.0176, which is quite close to 5% now. All right, now next I'm going to try my luck again using 11. Okay, so using 11, of course you have to use your calculator to calculate this. Right, now using 11, that should be 0.0592 here. Right, 0.0592, which is already outside of the significant level or the rejection region there. Therefore, here I can conclude that my critical values. So my critical values are anything more than 11. So it should be 12, 13, 14, and 15, since there are 15 observations there. All right. Okay, now I hope that is clear. Once you have done the setting up of the critical values or critical region now, the next part will be to go back to your sign, the sign that you have set up. Now in my case it's through my Excel sheet here. Okay, so I'm looking at a positive sign because it's greater than. So I'm going to count how many positive signs are there, which means those house martins that is above 270.5. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12. Right. So my value x in this case, number of observation that is greater than, I have x equal to 12 based on my data that I have evaluated. So the x is actually 12. Sorry, here I should be using a lowercase x here. The discrete value is 12 here. Right. Now next thing would be I need to check whether this 12 actually fall in the critical region or critical values here. Does it fall in the critical regions or not? Yes, because 12 is in the critical region. So therefore, we will have sufficient evidence to reject the null hypothesis. Therefore, we can conclude that number of house martins flying over is greater than 270.5, or you can say that the number has already increased. All right. Now I hope that is clear. That's how we carry out the non-parametric sign test. First example. All right. Now stay tuned for this next example. All right. Let's look at second example here. Now it is known that from the previous trials that with a fully charged battery, a vacuum cleaner will be able to clean for a median time of 27.35 minutes before the battery runs out. Now the manufacturer is testing a new type of battery to see whether the cleaning time is different. Now the cleaning times for a random sample of 9 occasions with the new battery rounded to nearest 1 decimal place are as follow here. Alright, now we need to carry out a sign test to examine at a 5% significant level whether there has been a change in the average cleaning time. Okay, so the time durations that it take for the vacuum cleaner to be able to last for that long. Right? So as usual, by using all the data observations, you can create the sign here just to observe. You can see that majority of the time durations is above the median time, which is 27.35. So here we have 1, 2, 3, 4, 5, 6. We have 6 data observations that is above 27.35 median time. All right. Okay. Now, as usual, we can write down our hypothesis statement here. Right. So here we are going to test at 5% whether there has been a change in the average cleaning time. So here we can say that the average cleaning time is or is the same. It's the same as 27.35 minutes here. Right. And then our alternative statement would say that the average cleaning time has changed. Has changed meaning that it could be less than, it could be greater than. So here we will say the average cleaning time is difference. Is different than 27.35 minutes. Yeah, right. So they are different, right? Okay. So once you're ready with this, as usual, we need to label because this is a binomial distributions again. Okay, so we have sample size of 9. Okay, this is a binomial distributions. You have to sort of specify the representations for the discrete variable here. Okay, so x actually represent number of sample that is um, greater than, take for instance, right? We will say that number of data observations that is greater than 27.35 minutes, right? So we want to look at how many actually greater than 27.35. Can I also represent x as a number of data that is less than? Yeah, by all means, you can do that, right? So based on the sample that we have collected, we have 1, 2, 3, 4, 5, 6. So we have 6 sets of data um, that has time greater than the median time, 27.35 minutes there, right? So this is what we found out, right? Okay, now again, we're going to use trial and errors here. Okay, because this is difference, so it's actually a two-tailed test. So this is two-tailed. You can say that this is a two-tailed test. Okay, so which means we have to have our um, upper critical region and then our lower critical region. Right. So for our lower critical region, we can try try and error, for instance. So we can try, um, let's try with px less than a 1 then, for instance. Okay, just let me get my calculator there and then see. Okay, x is equal to 6. Let me clean this up first. We'll use that in shortly. Okay, so this is sample size of 9. Okay, we are looking at the lower boundary first. So anything less than a 1, for instance. Okay, so anything less than 1 is 0.0195. Okay, which is still in the rejection region of 5% here. Then I can try px less than 2 then. Okay, so using px less than 2, let me see. So px less than 2 is 0 point, oops, sorry, I accidentally closed my calculator. Hold on for a while. Okay, all right. So px less than 2 is exceeding the critical region that is given by 0.898. This is greater than 0.05. Which means x equal to 2 is outside of the rejection region. Okay, therefore our lower limits will be 0 and 1. Okay, lower limits will be 0 and 1. And then next we're going to test the upper limit now. Okay, hold on. We're going to test the upper limit. Okay, so upper limit, now because binomial distribution is symmetrical, right? So if the lower limit is 0 and 1, most probably the upper limit will be 8 and 9 then. So just out of curiosity, we can try like x greater than 8. You can actually give it a try. So for instance, greater than 8. So let's see 8 then. So if it's greater than 8, we have 0.0195, okay, which is still less than 5%. So therefore, you can try like 7. So px less than 7, sorry, px more than 7. has already exceed 898, exceed 0.05. Therefore, the critical value or critical region here, here I try to use both terms by simplify here. So it will be 0, 1, and 8 and 9. So this one will be our critical region, right? Now going back to the data that we have collected just now, we have x equal to 6 here. We have 6 sets of data that is above the median time. Okay, above the median time. So we're going to look at 6. Is 6 in the rejection region or not? 6 is outside of the rejection region. Therefore, we don't have sufficient evidence to reject null hypothesis. Therefore, we conclude that the average cleaning time is still the same as 27.35 minutes there. All right. Now I hope that is clear. All right. Now I'll move on to the third example shortly. All right. Welcome back. This is example number 3. Now, the median time it takes to cure a particular illness using standard drug treatment is 23.5 days. A new drug is being tested to see if it reduces the treatment time. A random sample of 50 patients with illness is selected, and the patients are given the new drug. Of these 50 people, 33 are cured in less than 23.5 days. We need to carry out a sign test to examine at 10% significant level whether there is a reduction in the median time required to cure the illness when using the new drug there. Right. Now, as usual, we're going to start off by stating our null and alternative hypothesis. So first of all, we'll say that now the median time required to cure the illness, median time required to cure the illness. Okay, so median time to cure illness. This particular illness is 23.5 days. And then whereby our alternative will state that the median time has reduced. The median time to cure illness has reduced. Okay, has reduced, is less than 23.5 days. Okay, so those are our hypothesis statements. All right, so we are good with that. Okay, now next we will have to the same thing. We are going to identify our x. So what does the x actually represent first? So the x actually represent number of people. I would say number of people. All right. So number of people that has cured in less than 23.5 days. Okay, so number of people that has been cured in less than 23.5 days. Right. So that is why it's x, and then x can be represented as in a form of binomial distributions. Number or sample size is 50. Probability of success will be a half here. Right. Okay. All right. Now I hope that is clear here. All right. Now because the sample size is larger than 30 here, right? Now therefore for convenience purpose, right, not because we can't continue with binomial distributions, but but for convenient purpose, we can approximate this binomial distribution using normal distribution. Right. Now the criteria for a good approximations will be the NP must be greater than 5. At the same time, the NQ must be greater than 5 also. So by using this value, it's quite obvious that the number of trials multiplied by P is greater than 5. The N multiplied by Q is also greater than 5. Therefore, it's a good approximation here. Right? By using the um, approximations, so we can convert this binomial distribution using normal distributions. Right. Now, normal distributions will have a mean of NP, which is actually 25, and then whereby the um, variance will be 25, that will be a 12.5 here. Right. So therefore, this can be approximated using binomial distributions of mean 25 and variance of 12.5 here. Right. I hope that's clear. Okay. All right. Now next, as usual, because the alpha given to us is 10%, so 0.10. So 0.10. In order for us to be able to reject null hypothesis. Okay. Now we want to find out probability of x that is more than or equal to 33. So if there are more people, cured in less than 23.5 days, therefore the chances of rejecting null hypothesis is greater. So we have a significant evidence to suggest that we can actually reject null hypothesis. So we are interested to find x greater than or equal to 33. But because we are using a normal approximations, so therefore we are going to use normal approximations here. Okay, by using normal approximations, we are indirectly converting a discrete distribution into a continuous. Therefore, don't forget to carry out the continuity correction. So continuity corrections would be 32.5, and then we need to minus off the mean here, and then divided by the standard deviation. Okay, and then there you have it. Okay, from my calculator, I'm going to try to calculate this. Okay, so the mean is given as 25 in this case, whereby the standard deviation is square root of 12.5. Okay, so that's how it looked like. I'm interested to calculate more than, so more than 32. So here I'm going to test it out, 32.5 in this case. So based on the calculations, is it more than 32? Probability that is more than 32. So that is actually equal to 0.0169. Okay, and then this 0.169 is actually less than 10%, less than 0.1, because this is 10%. Now therefore this is in the rejection region. It's in the rejection region. Therefore we have sufficient evidence to reject H naught. Okay, rejecting H naught meaning that median time to cure illness is actually less than 23.5 days there. All right. Now I hope that is clear at this point. All right. Now of course, using software is quite easy in this case. All right. In the exam, you have to use your data booklet. So all you need to do is just calculate this value. Okay, and then you're going to look in your MF19 to locate this particular value here. Okay, so just let me give it a try to calculate this value, and then I'm going to show you how to actually use your data booklet. How to use your data booklet to actually get the same answer here. Right now, before that, let me calculate that answer first before we let me get the 0.5. Okay. All right, and then um, let me see. That will be 7.5. Okay, so if you use your manual way of calculating, this probability will be P uh, PZ. Okay, sorry, this is Z actually. I think I made a mistake here. Sorry, that is actually a Z. It has been converted to Z score. So I need to change this. Now, therefore, this is a Z greater than 2.121. Okay, 2.121. So therefore, I'm going to refer to my MF19 data booklet. Okay, let me see. Okay, my MF19 data booklet. Now, the sections that you're supposed to look for will be normal distribution. So I'm supposed to look for normal distribution. Okay, somewhere here, yes, correct. So normal distributions. Under normal distribution, I'm supposed to look for 2.12 approximately. So 2.12. Yeah, 2.12. Okay, so 2.12. This is 2.12 somewhere here. Do you see that the number is actually 0.9830? 0.9830. Okay, but because the region that is shaded in the data booklet here, you can see that it's actually on the left hand side. Therefore, I will need to take this number here, 0.9830. So I will need to take 1 minus 0.9830, which is actually 0.0170, which is approximately the same as 0.0169 then. Right. So I hope that you know how to actually read the data from your data booklet here. Right. But the conclusion will still stay the same. Right. So stay tuned for the next example.